So this is going to be the solution to the third challenge problem of the third general problem set. Um, yeah, I want to present this because it's a very good showcase of like it's a very pretty solution. And there's a lot of things we had to do to really reach it, but at the end, it's a pretty fun solve. So what you have is a triangle ABC with the like the angle C being 60 degrees, BC is being 4, such that like so D is like in the middle, is the midpoint. Um, so yeah, BD and CD are both 2, and they want you to maximize the value of tangent of BAD. So really, the main strategy, right, when you look at something like this, is to try and find like a function for BAD, tangent of BAD, and then try to bound it, right? We know how to find min-max of functions, right? That's calculus. The solution itself, like the one that's just easier and cleaner, it's not going to require calculus. So, and I'm going to be showing that. But when we find f of x, all of you who've taken calculus, you guys should be able to do it. Um, and again, we're also going to use this formula here. It's not like super niche, but I guess if you haven't paid attention in class, it's usually not always. It's not, it's okay if you don't remember it, right? Okay, so the first step really, we want to find tangents. So it makes sense for us to do what, like draw right triangles, right? Because in trigonometry, basically every uh, trigonometric function is just from a right triangle, like sides of a right triangle. Okay, so what you're gonna do, we're gonna drop an altitude from D down to AC. I'm gonna call this point D prime, and same thing with B. And notice, right? What you essentially get is a right triangle, um, AD prime and ABB prime. And from these right triangles, we get these two angles here, BAD and DAC. Um, all right. So, like, you know, from the 60 degrees and the side length of 2, these both of these two triangles here, they're just uh like they're 30, 60, 90 triangles, which means we actually know D prime, this length here is going to be root 3. This length here, BB prime, is going to be 2 root 3. And CD prime is 1, D prime B prime is 1. And right, we need to find a variable for the f of x, like the x variable, to minimize and maximize. So we're going to set AC's length as x, okay? Now, the tangent of DAC, or CAD, however you want to write it, it's going to be what? It's going to be the opposite over the hypotenuse. So it's going to be root 3 over x minus 1. And by the same logic, tangent of BAC is going to be 2 root 3 over x minus 2. And this is where it comes in, right? Okay, so BAD is just, what is BAD? It's just the difference between these two. It's equal to tangent of BAC, the larger angle, subtracted minus the smaller angle, CAD. And then using this here, we're gonna derive a function, right? So that's just going to be BAC over 2 root 3 over x minus 2 minus root 3 over x minus 1, all over 1 plus 2 root 3 times root 3 over x minus 1, x minus 2. I'm not going to do the simplification here, but you should end up with root 3, x root 3 over x squared minus 3x plus 8. And that's your min-max function. So at this point, people who've taken calc, you can just do the calculus method. I will say you're going to end up with a really ugly uh, thing that you have to simplify, and it's just very tedious, and I don't like it, right? So in this case, I'm going to present a different solution, and it's going to involve a algebraic inequality called the arithmetic mean geometric mean inequality. So what is this? It's a result in math. Actually, we've done this in the last weeks, like general problem set 2. One of the proof problems, we actually showed that this is true. But the basically it says the arithmetic mean of two numbers is always greater than the geometric mean. And yeah, we guess x plus y is greater or equal to 2 times root x y. And let's see how we can apply it here, right? So first of all, let's set f of x to some k value, and then we want to maximize k, right? Okay, so uh, x root 3 over x squared minus 3x plus 8 is equal to k. We're going to try and make this easy so that we can apply this. Really, when you want to apply this, hopefully your other side, one of your sides is going to be a number, because only when your other side is an actual number can you find a literal bound, right? You can't bound a function by like another function. It just doesn't, well, I mean you can, but like it doesn't help. Um, so what we're gonna do is we're gonna flip this thing over, and then we're gonna move the 3 to the other side, and you get root 3 over k. You can work this out on your own. And then we're going to divide directly by x, which gives us x minus 3 plus 8 over x is equal to root 3 over k. Now, we're going to add the 3, so x plus root 8 over x is equal to root 3 over k plus 3. And here, right, the arithmetic mean of two numbers, x and a over x, is always greater than than its geometric mean, which is this. Square root of x times 8 over x. And guess what? The x's cancel out, so you actually get a real value, which you can then evaluate. 2 root 8 equals 4 root 2. Now you have an inequality with k and just a number. So now you can just, now all you have to do is solve for k in this inequality. So root 3 over k plus 3 is greater or equal to 4 root 2, right? Um, some inequality tricks later. Root 2 minus 3. Okay, when you flip k, you have to flip the sign as well. This is just a property of um, inequalities. I mean, you can test it out on yourself, plug in different values of k. It's always going to be like this. And when you multiply root 3 over, you just get k is less than or equal to root 3 over 4 root 2 minus 3. What was our initial problem? We wanted to find the max value of k. And guess what? We have a bound on the max value of k. It cannot be greater than this value. So actually, this root 3 over 4 root 2 minus 3 is our solution. And yeah, that is it. We are done with the problem.